Okay, this is a VanDeGraaff machine. It's an electrostatic machine. Um, Lots of different variations on this theme. A lot of different ways to make this work. This is homemade. Something I built, oh gosh, I think 20 years ago, thereabouts. I'm not going to get into so much of a demonstration of what it does here, but more of how it does it. It was made look familiar to folks that have seen these things before. There's a toroidal terminal up top, an insulating column through which a belt passes. Some potential rings here, we'll get into that later. Base unit, motor in there, which drives the belt. And basically what it is a charge pump. There are, as I said, many variations on this theme, how they work. Typically, they would be self-excited, meaning that it, through friction, generates a electrostatic charge on this terminal. This one marks a little bit different. It is not self-excited. It has a little high voltage power supply in there that sprays a charge on the belt that accumulates in this terminal up here, which is not just a toroidal. It's made of cardboard and foil, aluminum foil tape. This bit is dryer ductwork, something like that there, but a flexible aluminum stuff you get at any hardware store, and a cardboard frame, sort of like a rim on a wheel that supports the whole thing, and it's all taped up with aluminum duct tape, and that just sits on here. It's very lightweight, cheap to make, easy to ding. I've got a ding there. You just put some tape over that. Another one here needs to be fixed. This thing's been sitting in storage for a while, so it needs a real good cleaning. The slightest bit of lint on the terminal really does reduce the voltage that can accumulate on there, which typically is, could be a couple of 100,000 volts, and if conditions are right, even up to 1 million volts of potential on this. Now, interestingly, it's fairly innocuous as it is. These kind of voltages are very low current. The capacity of this to store a charge is quite small. You can have a 12-inch arc jump from this terminal to your hand, and the most you feel is slight, like a pin prick. There's no real shock to it. Although there are some things you can do that could prove lethal if you're not careful, but as it is, it's not going to hurt you. As I said, there's a high voltage power supply down in this base. It sprays a charge on a belt that's running inside of this tube. That charge gets delivered to the terminal. This is just a piece of thin-walled PVC pipe. It's not Schedule 40, although you could use that. It would be no problem. The diameter I chose, I chose it because this is what I had handy, along with the fittings that I needed. Ideally, you probably want something of a larger diameter for that. There are issues with it being so narrow. We'll get into later. The point of these rings here, I'll close up on them a little bit later, is to equalize the potential along this pipe. I mean, you're talking about hundreds of thousands of volts up top here and ground. And you want that to be fairly equally distributed along this pipe. And these charges are enormous, and they can accumulate on these outside surfaces of this column and cause problems. Not the least of which is that sometimes it makes the belt pull out inside of here, and because of electrostatic attraction to the outside surface, the belt's trying to discharge somewhere, and it'll do so in the most convenient place, and if it happens to be inside this tube, it'll do it. And so that's a problem. That's what these rings are. Again, more detail on those later. They're just pieces of copper wire twisted around there with corona points. Nothing mysterious really about that. So you can see the terminal just kind of sits on there. It's not attached. There is a wire lead that you would normally attach to the foil here. Piece of masking tape or whatever holds it close. At these voltages, it does not really need to be actually touching it. Indeed, I'd forgotten completely about it and just had it tucked in, and the thing still works just fine. So I'll leave this off. What I really want to do here is show what's inside the thing. How the heck does this work? I think I can do that reasonably here. So start with what's down in the box, down here. It's got a couple of toggle switches, nothing mysterious, a couple of pilot lights. One toggle energizes the motor, that's what transports the belt, and the other toggle switch turns on the internal high voltage supply, DC supply, that sprays charge on the belt. And so rearrange the camera a little bit and get into a bit more detail of what's down inside there. Okay, before we get into the internals of this box here, this is a larger terminal sitting over yonder in the previous clip. This has roughly about 10 times the capacity of this one, and what it does, even though it has a larger radius, does not really accumulate much highest voltage as the smaller one. Difference with this one is because it has higher capacity, packs a bit more of a wallop when you get an arc to you. It's not harmful, nor painful, just it's noticeable quite a bit. You actually get a jolt from it. No great advantage with this. It's made of aluminum coated mylar, I think, with a helical coil. It's ductwork stuff. Conductive enough for this work. The frame, again, is just made of cardboard, sort of like a wheel rim would be, just to hold the thing together. Yeah, it serves its purpose. The other thing, a little bit more about the belt. Initially, when I first built this, I used this tape. It is a nylon reinforced, I guess you'd call it celluloid tape. As you can see by the condition of this roll, that tape has issues. It is hydroscopic. It absorbs water readily, It's pretty tough stuff as far as stretching goes, and that's why I chose to use this particular stuff. But it, basically it's two pieces of it, sticky sides to sticky sides, to make the loop, the belt. And it worked okay. In spite of its high, propensity to absorb water, it's a fairly decent insulator. But the belt made from this was very noisy because of the lumps and wrinkles and things with it. Just it's not the best stuff. It's a good start. Back when I made this, you couldn't just get on anything.com and buy a VanDeGraaff belt for a custom made length. It's just not happening. So this is a 1-inch wide stuff, and it did work, but it was not the best choice. What I ended up with was Kapton tape. This is 3/4 of an inch wide. This is a new roll, and basically the same thing. I just stuck two sticky sides together. The adhesive on this stuff is very, very good, long-lasting. The properties of this material, insulator, it's an excellent insulator. It's very heat resistant. It's got a fairly high dielectric constant. It's a very good insulator. Exactly what you want. It also doesn't stretch very much. I made 3 belts for this. This has been through quite a few permutations, materials and pulleys, materials, motors, and so forth. But what's in there currently is this Kapton tape, and I guess I had said that this was something like 20 years ago, more like 30, and about 20 years ago is when I started using this Kapton tape. I made 3 belts, and all 3 of these have been tried, including the one that's in there right now. These belts are used and are in perfect shape and condition. Not a wrinkle, not a crease. In fact, here you can see where the splice is. I'm not going to get into how I made these. Trust me, it was a kind of a pain in the ass, but I did get them done, and they work very well. I would have liked to have a belt made of this material that was maybe 2 inches wide, maybe more, maybe multiple belts in one machine, who knows. The width of the belt is kind of what determines the amount of current you can get out of the terminal, and there's the voltage that it will accumulate. That this belt is only 3/4 of an inch wide, and does what it does is, to me anyway, truly amazing. So, get this guy off of here. This weighs nothing. I just let it roll over there. And I guess it'll probably be better to get the camera a bit closer, to zoom in on some of the details of the collector up here, the pulley, and what's going on down in the bottom. Yeah. Okay. I initially had said I wasn't going to do an operational demo of the thing, but in spite of the fact that I've not cleaned the spider webs and dust off of it, and its relative humidity right now here is above 50%. Usually doesn't work so well when it's wet, humid. 50% is about right for domicile, but lower RH is better for these beasts. But, you know, since it seems to be working fairly well right now, just as it is, before I open it up, I'm going to fire it up and show a little bit demo. There are two switches on it to control power. One of them turns the motor on. You'll hear that as soon as I turn it on. And it's just a motor that makes the belt travel up and down. The other one is the high voltage supply inside that sprays the sprays the belt with a charge. More on that later, but the charge is a positive one, so that this terminal will be positively charged. And judging by the radius of this, my wrist, and the length of the arc, it's probably going up to, maybe 80,000 volts or so, to demonstrate. Well, gee whiz, I guess I actually have to have the thing plugged in. Pardon me. And that's the problem. Don't need this lever. There? Good. Alright. Now we're on. And that's just the motor running the belt. It does self-excite a little bit. Just some friction on the pulley. There's some arcs, maybe an inch long or so. Now I'm going to turn the high voltage on. You'll hear a hiss, and that's the corona discharge that are happening between the spray brush and the pulley in the bottom. All of these corona points, and this terminal will discharge out into the open air without anything being drawn near it. Typically, because of its location, it's going to discharge over to that, in that direction. It's not going to be so much seen as heard. High voltage on. Now, I know there's no way to see it. I'm looking at it here. There's fluorescent light on above. And that arc can, I can see where it's coming from, but it's very, very, very faint. No way to capture it on vid. And it's interesting, every time it arcs, this changes position slightly. Now you know as I draw near with my fingers, it stops popping because it's now discharging into my fingertips. You might be able to hear the whistle arcing corona. But if I present a broader radius, this works much, much better when it's really, really dry. Humid-wise. It might see me twitching a little bit, but it's quite painless. The most inconvenience is where the arc taps you. It's like a tiny pin prick. It's harmless. Yeah, it looks like about maybe 5 inches. Figure 20,000 per inch, roughly, maybe more. You can see the whole column and terminal shaking because it's drawn to me until it discharges, and then it's not drawn to me, so it kind of rocks. another thing about this is prolific amounts of ozone produced by it, especially when you're not drawing arcs from it, from what it's doing right now. Pop, 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 pop. Oh, it quickly fills the room and it becomes irritating. It's funny too, I've noticed that after it's been working a while, it seems to work better. When I'm full, what, 7 inches away, and it's 50% humidity or so, and it's drawing pretty good arcs. In spite of me having not cleaned it yet. And of course it presents a smaller radius to it. It discharges and leaks off as opposed to a large radius. You can feel the hairs on your arm reacting to it. It's sort of like a voltmeter. But there's an arc, like a corona discharge happening between each of these wires, each of these points, which gives it a sort of a voltage gradient over this. One of the best things that I did was to add these. It's a simple solution that made a heck of a difference. Okay, turn the high voltage off, discharge the terminal. It still self-excites a little bit. Surprising. It's not supposed to do that. Turn the motor off. Take this out. And now, finally, we'll get on to the inside of it. Okay. So, what's inside of this beast? A heck of a lot. A couple of screws. This cabinet used to be a security alarm system that was retired. It was something I used to do in a former life. Made a handy cabinet for this. I did have to make a panel, this aluminum plate over the top to cover up some holes from previous permutations of this. And it's hinged. This used to be a panel that would hang on the wall. Had a circuit board in it and some controls and things, like a keypad, some cheapy alarm system, and made a pretty good cabinet for this project. And let's see the top half. A couple of toggle switches, pilot lights. The motor that drives the belt. That used to be a blower motor from a microwave oven. And, just about the right size. It's 3600 RPM. There's a home-fashioned pulley on it, which engages this Kapton belt, which I described earlier. The pulley here, in this case, is made of wood. It's made of plywood. I did experiment with a number of different materials. It does matter what you use here, depending on whether you want it self-excited or externally excited. Get into that later. For my purposes here, the best choice was wood, which, while it's not the best electrical conductor at these voltages, it kind of is. Think of it as a resistor. it's conductive at these voltages, but does offer some resistance. Rubbing up against the belt, just barely touching it, is a Corona brush. It's a braided copper wire here. Let's see if I can get the camera down in a little bit to show a little bit more detail of that. And I'm having some problems with my lighting here. So pretty simple. Shaded pole motor drives the belt. The pulley at the other end is aluminum. It's very conductive, and we'll get into that later. Basically, what's going on here, there's a power supply down here that supplies a high voltage through this wire, and there's a resistor, and then that resistor is in series with the Corona brush. The purpose of that resistor, and the pulley being a resistor itself, is to limit the current. You don't want arcs forming here. You want a Corona discharge, a brush. It's has the appearance of like a purplish glow when this thing is in operation, coming off of this brush, spraying charge onto the belt. It spins in this direction. The belt comes down. Just as it leaves this pulley is where the charges are sprayed onto it. Now, in this case, the charge is a positive one, meaning it sucks electrons off the belt, off of the outside surface of the belt. The inside surface of the belt, being in contact with this, let's call it conductive pulley, is at ground, or earth, neutral, if you like. So what that does is it causes a positive charge on the outside of the belt as it heads up the column, and a neutral charge with respect to ground, earth, on the inside of the belt. Those two opposing charges are what causes the charge to stick to the belt. If both sides of the belt were charged equally, the charge would just fly off and you'd be left with nothing. But there's pretty much a neutral charge on the inside of the belt and a high voltage positive charge on the outside of the belt, and that gets sent up the column to the terminal. How that gets stripped off, get into later. Doesn't. But for the purposes here, what's going on down here? Charge sprayed onto the belt. It does self-excite, even with this wooden, moderately conductive pulley. It does self-excite, meaning the only thing really required to accumulate a charge on this belt is the separation of the materials. I've experimented with different materials for the pulley, trying to get the thing to self-excite. I've had mixed success depending on what pulleys I was using. I've used lucite, ABS, plastic, styrene, and other things. I've used metal pulleys down here. But for this externally excited design, the wooden one seemed to work best. And I have a pretty good idea why. It's because it does enable a neutralization of the charge on the inside of the belt. That is the part of the belt that contacts the pulley, versus the charge sprayed on the belt from the outside, on the outer side of the belt. Seems to work pretty good. I've experimented with all kinds of positioning of this brush, the voltages applied to it, the amount of current supplied to it, and various speeds. It's possible to slow these motors down. It's also possible to speed them up. Right now this runs 3600 RPM, which is its design RPM. I've sped it up, I've slowed it down. It seems like speeding it up detrimental for some reason. It's almost as if it slings off the charge. I don't know, but higher belt velocities intuitively would seem like a better thing, but there are limitations to that. Slower velocities, that didn't work very well either. It's easy to slow these down, and that didn't work. So it seemed like 3600 RPM, at least for this configuration, was pretty much optimal. The voltage that's sprayed onto this belt is about 25,000 volts DC positive. There's, like I said, current limiting resistor in here. That resistor is 66 million ohms, 66 mega ohms. Interesting, that came out of an old color TV set. I think it was a focus dropping resistor for the picture tube. But it's I think 2 watts, and it does warm up. It's encased in a natural rubber tubing to serve as insulation. I don't want arcing to happen. Keep in mind, there's 25,000 volts on that. I don't want arcing to happen between it and the casing or anything else here. I don't want corona discharge, purple flame. I don't want any of that. The only place I want corona is right here, spraying on the belt. And it's pretty well behaved in that regard. There's a plastic shield here to help keep it from arcing from this brush to the motor frame, which is grounded, of course. Plastic standoffs. That used to be a screwdriver handle. Just convenient. This bit here is a wire insulated that just serves as a tensioner. Probably should have put gussets on this mounting bracket for the motor to stabilize it. I didn't. Turns out might not have been the worst idea because of this wire, the tautness of this wire here. I can control the tensioning on this belt precisely. Not that it matters a whole lot, but just in the interest of making the belt last as long as it could, and being able to accommodate slightly different lengths of belt, being that they're handmade, this turned out to be a pretty good deal. Now, this high voltage supply down here, you see, I'm going to get a better camera angle. Okay. Maybe not the best angle. But that'll do for now. Power entry module, that's where the 120 volts comes in. Your regular line cord plugs into that. Of course, the ground, safety ground, is connected to the box. There's a circuit breaker. I think it's 2 amp. Just as a safety thing. More to protect the electronics than me. A laminated core transformer takes the 120 volts in from the line, knocks it down to 24 volts AC. That 24 volts AC goes onto the circuit board, my design. Even that's pretty simple. There's a rectifier, full wave rectifier on here, some filtering, little filter caps. There's a 12 volt voltage regulator on here, and he supplies power to the oscillator, which in this case is the ubiquitous 555 timer. It's wired in as an asynchronous oscillator. Nothing mysterious about that. Fixed frequency. In this case, I'm running this at 17 kilohertz. The flyback transformer, the step-up transformer, and the cascade tripler that I'm using, both were paired. They came out of a computer monitor, an old monochrome computer monitor. That thing ran at 15 or so kilohertz, but for some reason this seems to resonate better at 17, so that's the frequency I chose. It was determined by experimentation. The odd thing about this is that most of these flyback transformers I've run across have multiple windings on them. This one just has a primary and a secondary. The low voltage primary, which in this case would be about 150 volts, and the high voltage secondary, which in this case is 8,000 volts. I didn't want to have to work with something like 100 or 200 volts of supply to this. So I couldn't use the original primary winding for that. So what I did is I wound my own. That's what this is here. That's 35 turns of number 24 gauge enameled wire. Nothing special. And it's kind of neat because there were so many unused terminals on this guy. I could just wind it and solder them right to the terminals. I ended up using the original primary from this transformer to drive the indicator for the high voltage. So I'm not just, when that light comes on, I know it's not just that the power has been applied to the high voltage section, but that the thing is actually supplying high voltage. So that kind of extra benefit to having the original primary on this transformer and using it as a secondary just to drive an indicator. And if that indicator's lit, I know that the circuit driving this transformer with my home wound primary is working. Nothing mysterious at all about this. The AC, 8,000 volts AC, comes out of this transformer and goes into this cascade multiplier, this green bit down below here. And that not only rectifies it into DC, but it steps up the voltage even more. In this case, to about 25,000 volts. And that's what comes out, goes through the resistor and into the corona brush. Over here, a little hard to see in this lighting, I reckon, but under here is the switching transistor that actually switches the power into this transformer. It's a square wave, approximately a square wave. That transistor is a MOSFET, high voltage MOSFET. It's got foil over it to shield it from any kind of corona discharge, because those things are, these MOSFETs are sensitive to high voltage, especially on the gate. But the gate's directly driven from the 555 timer, issuing it a square wave, and that switches current through this primary winding, about 24 volts DC, thereabouts, maybe a little more. And this steps it up, 8,000 volts out of here into this, the tripler, 25,000 volts out or so out of that into the corona brush, and it sucks electrons off of the outer surface of this belt and sends that charged situation up to the top terminal. And really, that's where most of the magic happens. Alright, I did say I wanted to get a closer view of this brush here. This is the one that sprays the high voltage onto the belt here. It travels this way. Belt goes around the pulley. Just as it leaves the belt, there's this corona brush. Again, it's just a piece of braided copper. Nothing special about it. I could have used a single point there. I tried different things. It didn't seem to make a heck of a lot of difference. But this one, because it's so flexible and it has so many little points, seemed to do better. And it didn't mess up the belt, didn't scratch it. Parts of it may be actually in physical contact with it, but that's really not necessary. I bet it be so. Now, normally, the motor has to be running before the high voltage can come on. There are two separate switches for that. I have disconnected one of the legs of the motor supply. So the motor's not going to run, and by this it'll allow me to turn on the high voltage just to do a quick demonstration. I don't want to leave it on too hard or too long. I've had problems in the past with it damaging belts. Not these Captom ones so much, but I'm not going to take too much of a chance with that. What I would like to show here before we get to the top terminal is how this corona discharges. As I said, this is 25,000 volts here, DC, 25,000 volts positive DC with respect to ground in the case. And yeah, you'll be able to hear it hiss, the corona discharge hiss. Main power's on right now, and ordinarily the motor would be running, turning the belt. As I've said, I've disconnected the motor, so all we're going to get is high voltage as soon as I turn this switch. You'll hear it, and hopefully you might even actually be able to see some of the purple glow that is a corona discharge spraying charge onto the outside surface of this belt. That is high voltage on. You can probably hear that, I hope. And there's a, well, it's visible to me here even with the lights on. But, oops, right about down in here, you can see it. You see this arc coming to my pointer? Oh, by the way, yeah, that's 25,000 volts. I can kind of feel it. But you know, I can stick my finger right up to it and draw an arc right to my finger. It's quite painless. You know, yeah, a little bit of RF burnage. Nothing we can't handle. Harmless. And as this belt passes through this gap between the pulley, which is near ground, and the high voltage brush here, the belt picks up and carries that charge up the pipe to the terminal, upon which it will be delivered. That, like I said, it's quite harmless. Anybody that has been zapped by the EHV on a TV kind of knows what this is like. It's not going to hurt you. This ain't. Although there's some heat, you know, little point source heat on where it arcs to. But yeah, not going to hurt you. Not much. So, as promised, I did want to show, you know, the belt charger down here, active. And next, we'll show what happens up top. Like I said, that's where the real magic happens. Down here's nothing. Have a look. Alright, here's the top. The collector up top. This is where the toroidal terminal sits. There are two brushes up here. There's one up top and one here on the side. This here, that's the leading edge of the belt, so the belt's coming this way, up over the top and down the other side. What's going on here is that, now keep in mind there's a high positive charge on the outside surface of this belt and what is essentially a neutral charge with respect to the ground on the inside surface of the belt, that which contacts this pulley. This pulley on the top here is aluminum, very conductive, electrically conductive pulley. Actually, that was liberated out of a beater bar from a vacuum cleaner. And all these PVC bits here, including the pipe, were actually components used for a central vacuum system in a house. Very thin-walled, lightweight, and dirt cheap. So what's happening here? This brush is connected, electrically connected to the pulley. Here's the pulley's bearing, one side of it. There's another one over here, ball bearings. But this brush is connected electrically to that pulley. So what happens is, when that belt comes up with this high positive charge on it, on the outside surface, is taken off by this brush, this Corona brush, and it is fed to the pulley. Well, what that means is that once the belt gets up here, now both sides of the belt are equally charged, in this case with a positive high voltage. Well, then there's no more reason, the charge has no reason to stick to the belt anymore, because the other side of it is now the same polarity and potential as the outside of it. Both sides are the same. So that's what this second brush does. This second brush picks up the charge that's trying to get away. This positive charge is trying to get away from the belt because like charges repel. So this brush here is more or less electrically insulated from the pulley and this brush. And so it picks up that positive charge that's trying to get away from here and sends it up through this short piece of wire here. It's really not necessary to have this wire. The charges are so enormous, the voltages are so high that this just Corona sprays into whatever terminal you have here, even though the thing is mostly made of cardboard. And those voltages, cardboard's not bad. It's a resistor. It's not a great conductor, but it's good enough that this wire really need not be attached to anything. I do it because it seems to help a little bit, but so many times I just ignore it and put the terminal down, and this wire does nothing. It might help a little bit as far as current when you've got high humidity conditions, but with what it is here about now, 50% or so relative humidity, it works just fine even without this interconnect. In other words, this would be attached to the terminal, electrically attached to the terminal, but it really is not necessary. I could do away with it altogether. And that's how the top half works. So positive charge on the outside of the belt comes up, neutral charge on the inside of the belt. The brush picks up the high voltage positive charge, delivers it to the metallic conductive pulley, which makes both sides of the belt equally charged, and therefore those charges want to dissipate. They want to draw in electrons, and they're going to do that from this top brush, which is going to pull electrons out of the top terminal, leaving it with a net positive charge, and it's pretty high. This thing, I'm telling you, when you get to really optimal conditions, a little bit of tweaking here, a little bit of tweaking there, and the air is very, very dry, like you would get in the wintertime, to the point where especially to the point where the humidity is so low that it's uncomfortable. This thing will work amazingly well. I've seen arcs jump from the terminal all 4 feet down to the base, although normally it discharges out into the air and any metallic items that are nearby. There's a refrigerator sitting there and some ductwork over here and a ductwork above it, and there's a fluorescent light right above here that thing will light up. Even though it's turned off, it'll light up just from the electrostatic discharge happening all around the thing. And as I pointed out earlier, it produces copious amounts of ozone. It gets irritating pretty quick. Now, a word of caution: anybody that's attempting to do this stuff, I had an experience with this that was not good. I had the terminal on top, and on top of the terminal I had a Tupperware bread box. Okay, you know, it's a plastic box about the size of a loaf of bread with a lid. Well, I didn't have the lid, I just had the box. And I put the box on top of the terminal, knowing that I'd be able to charge the surfaces of that box. And I was in the middle of a demonstration while doing this. And me standing on the ground, being grounded, put my hand inside the box while the outside surfaces of the box were being charged. I really didn't understand that the capacity or capacitance or the ability for something like that to store electrostatic charge. I mean, I knew it would. That's why I was doing the experiment. That's why I was doing the demo the way I was. Well, I picked that box up off of there. I could have handed it to somebody. They could have handled it and without any bad things other than maybe a little bit of crackling. Well, I picked that box up and I was cradling it in my left arm, left hand, and I stuck my right hand into the inside of the box. Now, the outside surface, that is the bottom and sides of the outside of that box, were highly charged. And relative to the inside of the box, which was pretty much ground potential as it is. I was standing on the ground when I put my hand in it. I picked that box up. I put one arm on the outside surface and I reached in to the box. That thing shocked me. It almost knocked me over. The people that were watching it, fortunately very, very few people, saw the result of that. And it cured me of ever doing that again. You have to be careful about what you're charging up with these things. Yeah, with just the terminal on it, even a large terminal, that's the one you see sitting over here, even that, it's not going to hurt you. But certain materials, if you allow an electrostatic charge to accumulate on them beyond a certain point, will and can hurt you. Be careful. Please, 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 please. These are nifty things to fiddle around with. And not to mention that ozone's not exactly an innocuous gas. Yeah, not something you want to spend a lot of time breathing. Smells nice at first, like a lightning storm or a thunderstorm would do. But this it can get quite a bit annoying with that gas. So be careful. Have fun. I hope some of this makes sense to someone. Had a lot of fun with it. See ya.